Hello students, we shall see some examples of surfaces. The first example is that of a plane in R3. So example, plane in R3. So how does this become a surface? So let us try a figure first. This is x-axis, y-axis, z-axis. Now I have a plane. I am drawing a piece of the plane. Here is the point A through which the plane passes. This is a fixed point, and I want a kind of direction for the plane. So that is determined by two unit vectors that pass through the point A. They are perpendicular to each other and lying in the plane. So this is, let us say, vector P, unit vector. This is, let us say, the vector Q. The first vector is vector P, unit vector. Here is the vector Q. So correspondingly, you can look at the position vectors of P and Q. So this is P. This is vector Q. Both P and Q are transferred to the origin without changing their magnitude and direction. Now you take any point V in the plane. Take any point V in the plane. So look at the vector V minus A. That is this vector. So this vector is V minus A. V minus A. So V minus A can be written as a linear combination of the linearly independent vectors P and Q. So V minus A. So V minus A can be written as some, let us say, U times vector P plus V times some vector Q for some scalars U and V. So what is A? A was the fixed point in the plane. In the plane, and what are P and Q? P and Q are P comma Q are unit vectors. Unit vectors passing through the point A. They can be transferred, of course, to the origin. Passing through A and perpendicular to each other. And perpendicular to each other, lying in the plane. Both lie in the plane. Okay, so you have V minus A equal to UP plus PQ for some scalars U and V. So correspondingly, you have the ordered pair U comma V. U comma V. Now I am going to define a homomorphism from R2 to S. What is S? Our plane. And what is So here U equal to R2 and W is R3. So U2 S intersection W. S intersection W means S intersection R3, which is S itself, and the homeomorphism is this sigma of U comma V equal to so V was the arbitrary point in the plane. So V can be expressed as A plus U times P plus V times Q. Now, is this a homeomorphism? Of course, because vector addition, that is a continuous mapping. Scalar multiplication, that is also a continuous mapping, and their combination, that is also going to be a continuous mapping. So sigma is continuous. Is sigma bijective? Yes, of course, because sigma of u1 comma v1 equal to sigma of u2 comma v2 means that a plus u1p plus v1q will be equal to a plus u2p plus v2q. Both the vectors A cancel each other, and you have left with u1 minus u2 times vector P equal to v2 minus v1 times vector Q, but P and Q are perpendicular to each other, therefore they are linearly independent. So the scalars u1 minus u2 must be equal to 0 and v2 minus v1 must be equal to 0. That means u1 equal to u2 and v1 equal to v2. Therefore this sigma, this is injective. Now you check surjectivity. Surjectivity means you take any point V in S, you take V in S, correspondingly you can find, so look at V minus A, that is a vector in the plane. Every plane can be written as linear combinations of the vectors, vector P and vector Q. That means there exists U and V such that vector V minus vector A equal to UP plus VQ for the scalars U and V. This means that sigma is surjective. And already we checked the continuity of sigma. Now regarding the continuity of the inverse, how do we come up with a formula for the inverse? Sigma inverse of V. Take any point V in S, sigma inverse of V. So I must be able to express V. V is the vector, arbitrary vector. Of course, here also vector sign. Sigma inverse of V. So I want to retrieve my coordinates U and V, small u and small v. So how do I get this? See, look at V minus A inner product with the P. What you will get? You will get precisely U. And what is V minus A inner product with this Q? You will get V. Maybe I can write down. So what is V minus A inner product with P? It is UP plus VQ inner product with the P, right? UP plus V times Q inner product with the P. But P is a unit vector, so P inner product P is 1. So here U and Q and P, they are orthogonal vectors, it's perpendicular vectors. So Q inner product P is going to be 0. So I'll get U. Similarly, if I look at vector V minus vector A times vector Q, I mean inner product with vector Q, I will get V. So U and V can be retrieved by means of this formula. So I have V minus A times, I mean inner product with vector P, comma P minus A times, times means inner product with vector Q. So this is the formula for sigma inverse. Now inner product, that is a continuous mapping. Vector addition or vector subtraction, whatever, that is also continuous mapping. And you have continuous mapping at both the coordinates. So the ordered pair, that is also going to be continuous. So sigma inverse is continuous. Thus sigma is a homeomorphism. So this plane that is represented as R2. That's what. So U, the open set U of R2 is R2 itself. This plane is identified as R2. So this is the first example, and subsequent examples will be seen in subsequent videos. Thank you.